So maybe when we talked about RSA, some of you may have wondered about how, if factoring is hard, we have in the RSA crypto system, we end up picking two large primes and then multiplying them together. Right? So remember, in order to create the RSA key, the first thing you have to do is you have to pick two large primes. So you have to pick P and Q, which are both very large, so they might be a few hundred digits long. Okay? That's a very large number. So how do you test that it's a prime? Okay, so, well, it turns out that there's a very fast algorithm for doing this, except that it's sometimes wrong. Okay? So how does this algorithm work? So it's a primality tester. What you do is you input a number. Okay, so you input a number n, and it outputs yes or no. Yes, it's a prime. No, it's not a prime. Actually, it outputs yes or no. Yes, I think it's a prime, or no, I think it's not a prime. Okay? And sometimes it's correct, sometimes it's wrong. So it outputs either yes or no. And now, what are the chances that it's right? So the property so the property that this program has is that if n is prime, then it always says yes. Okay? But if n is not prime, if it's composite, then it doesn't always say no. Okay? Then it outputs no with some probability. Okay? And what that exact probability is depends upon how long you let this program run. Okay? So this question there? Sorry. Yeah. You had a question? Okay. So then it outputs no with some probability, which depends upon how long you let it run. So you can tune the probability. But let's say that you tune it so that the probability it answers no is 1 minus 1 over 10,000. Okay. So now, that's a pretty small chance of error. So now what you want to know is, of course, you don't know whether it was prime or composite. The question that you want to know is n prime or not? Okay? So you've input a number n, and you want to know with what probability is n a prime, right? So let's say you want to be 99.9% sure that n is a prime. Okay? Can you be sure if this is the case? Right? So the question we want to know is, question: if the answer is yes, does this imply that the probability n is prime is at least 0.999? Or, just replace it by anything, whatever you're curious about, 0.99. So what do you think? What's the answer to this? Yes? Does everyone agree it's yes? How many people think it's yes? How many think it's no? No, really? Why? Aha! Oh, that's an interesting thought. Yeah. But maybe Okay, so I'm asking about this particular number n. So what would you say about this particular number n that I had in mind? So n was a particular number. Let's say it was 91528320. Better end in an odd digit. Okay, so so I input this number n, and it told me yes. Okay, what's the probability it's a prime? Well, the answer is if it's, sorry, this was slightly tricky because if it's a particular number, then the answer is it's either a prime or it's a composite, right? So if it happens to be a prime, then the answer is the probability n is a prime is equal to 1. If it's a composite, then the probability it's a prime is 0, right? So we have to have a, so in order to make the question meaningful, we have to do what he said there, which is talk about what's the probability distribution on n, right? It's only meaningful if we picked n from some probability distribution and then we ask, what's the probability it turns out to be prime, okay? Okay, so we're going to come back to this question in a minute after we choose the framework in which we describe this kind of problem. So this kind of problem is an inference problem. Right? So assume that we knew that n was picked at random among all 200-digit numbers. So we just picked n randomly. We picked all the digits at random, right? 200 of them. And then we input that into this algorithm, and then we got the answer yes. Okay, now it's a meaningful question to ask, what's the probability n is actually a prime? Okay? And then we'll see what the answer to that question is. Okay? Okay. So now, the way that we can describe this kind of, all these inference problems is in a certain framework. So the framework is like this. So we are given two bins labeled 1 and 2. Okay? Each of these bins has some black balls and some white balls in it. Okay, so this one has some number of white balls and some number of black balls. So these are white, those are black. And in this one, there's a certain, some other number of white and black balls. So maybe in this one, this bin looks more like that. Okay? Okay, so let's say that the fraction of white balls in this bin was Q1, and the fraction of white balls in this bin was Q2. Okay? Now the question we are asking is, so we do an experiment. So the experiment is we select a bin and draw a random ball, a ball at random. And we look at the outcome. Okay, and suppose the question that we want to ask is, suppose that the ball happened to be white. Suppose we drew a white ball. Now we want to know, what's the probability that the bin that we reached into was bin number 1? Okay? See, the easy direction would have been asking, suppose we reached into bin number 1, what's the probability of drawing a white ball? It's just Q1, right? If we reached into bin number 2, the probability of drawing a white ball was Q2. But now we are asking the inverse question. We are asking the inference question. We don't know which one we reached into. Okay? And we want to know what's the probability that we actually reached into bin 1. Okay? Okay, but as we saw up there, to make this question meaningful, we have to say something about how we reached into the bins. So we have to say, we reached into the bins initially. So we reached into bin 1 with probability P. And we reached into bin 2 with probability 1 minus P. Right? So maybe P was 50, these were 50-50. So we just reached into one of these bins at random, and we drew a ball at random from one of these bins. And then we happened to see it's white, and now we want to know what's the probability that we actually, given that we reached in with these probabilities, what's the chance that what we actually picked was bin number 1? Okay? So why would we want to study such a problem? Okay. Well, in that example up there, bin number 1 is all the primes. Okay, so if you're picking 200-digit numbers, then this would be all the primes among the 200-digit numbers. Okay. Bin number 2 would be all the composite numbers among the 200-digit numbers. So in primality testing, bin 1 equal to the set of all primes of the length that we are interested in, of 200 digits. Bin number 2 is a set of all composites of that same length. What's Q1? So it's a probability, well, let's say white ball means yes. Right? So the test tells us yes. So Q1 would be 1. Because if it's a prime, it always says prime. What's Q2? If it's a composite, it still says yes with some probability. We said it says yes with probability 1 over 10,000, right? Because it says no with probability 1 minus 1 over 10,000. So it's 1 over 10,000. But this was not enough to tell us what's the probability we actually picked a prime. Right? To do that, we also had to figure out with what probability we input a prime to begin with. What proportion of numbers were prime. Okay? So P is equal to, it's the fraction of 200-digit numbers which are prime. So that's the problem we want to solve. So we are okay. If we knew this fraction, then what we really want to do is to say, suppose we do the test with this particular parameter. This is how good our primality test is. What's the chance that eventually, when it says a number, when we input a number and it says it's a prime, what's the chance that it actually means it? Okay. By the way, what's the chance that when it says no, that it's really a composite? If the program says no, what's the chance n is a composite? Yeah. 100%. I'm sorry? 100%. Does everyone agree? Yeah, because the only way it can say no is if n is a composite. Whenever n is a prime, it always says yes, right? So if it says no, it must have been a composite. Except sometimes it also says no. Sometimes when it's a composite, it also says yes, right? So, okay. Okay, so let's figure out how to solve this problem, right? So this is the basic problem that we want to solve, right? It comes up all over the place, right? So here's another place that might come up. So let's say that we are doing drug testing, we are testing a pharmaceutical drug, and we want to know how effective is it. Okay, so let's say that it's supposed to test for a certain condition, and now in order to figure out how effective it is, we look at two pools, two particular populations, right? So there's bin 1 and bin 2. Bin 1 is the population that's actually affected. Bin 2 is the healthy population. Right? So you divide the people into all the people, right, into two groups. Those who are affected by this condition, those who are healthy. And now Q1 is the probability that this particular test that we have designed comes up positive when we apply it to an affected person, right? So somebody who has this condition. And so let's say Q1 is 0.8. Okay. So we'd like this to be as high as possible. We'd love for this to be 1, but it happens to be 0.8. Okay. Q2 is the probability that the test comes up positive, even though you gave it to a healthy person. So this is a problem for us, right? So let's say Q2 is 0.1. So these are the false positives. Right? So, the test came up positive, but it wasn't supposed to. It's a bad case for us. Okay? But now, what we want to do, so the question that we want to answer is, suppose we administered this test to somebody and it turned up positive. What's the chance that this person is actually affected? Right? That's the question that we want to answer. Right? So we want to always turn this around. Okay? But in order to do that, we can't just do that in the abstract. We have to know what fraction were affected in the general population. Right? Because, for example, if we know that everybody is healthy, right? Nobody in the population is affected. When we apply this test and it comes up positive, we know that the person was healthy, right? So somehow, in order to make this inference, what's the chance that the person was affected? Given that the test came up positive, we have to know what proportion of the population was affected, right? If the proportion of the population that's affected is very, very tiny, then the chance, most of the time when the test comes up positive, it's because somebody healthy tested positive because of this 0.1% chance, right? So we really have to know what's p equal to fraction of population that's affected. And maybe this is a small number. Maybe this is 1 in 20. Okay, and then we want to figure out what's the probability. So what do we really want to figure out? What we want to know is what's the probability affected given that the test came up positive. Right? Okay, so in all these problems, so the common element is what we want to know is what's the probability of bin 1 given white. This is what we want to know. And what do we actually know? Well, what we know is what's the probability of white given 1. Okay, so these are things that we know. We know what's the probability of white given 1. We also know what's the probability of white given 2. And we know what's the probability that we chose bin 1. right? And now, this was a probability we chose bin 1 to begin with. But now, after we did the experiment, we are in this situation, right? Before we did the experiment, we were in this situation. We knew fraction p of, with probability p, we picked bin 1. Okay? We know that the fraction of people who are affected is 1 in 20, right? That's what p is here. But now, after having done the test, what we know in addition to this is that the test came up positive. And so given that the test came up positive, what do we know about the probability that we are in this case? Okay, that's the inference problem. Okay? Now, this is called Bayesian inference. Because what we are doing is we have this notion that we have this initial probability, a prior probability, right? Which says even before we start, we have this estimate saying the probability of being in bin 1 is 1 in 20. Okay, this is our prior probability. And then we make a measurement, we make an observation. And after this observation, we want to recompute the probabilities. Okay? And the recomputed probabilities are called the posterior probabilities. And that's what we want to try to figure out. Okay, so this was the prior probability. And this thing that we are interested in is the posterior probability. Right? It's after having done the experiment. Okay? And so what we want to do is we want to take this probability and express it in terms of those. And that's what Bayes' rule allows us to do. Okay, so what we do is write probability of 1 given white is what? Well, it's probability of 1 intersect white divided by probability of white. This is just by definition of conditional probability. Right? The probability that you reached into bin 1 and you drew white. But now, if you were to take this to this side, you would see probability of 1 intersect white is probability of 1 given white times probability of white. Right? But now by symmetry, you can interchange the places of white and 1. And so you could write it as probability of white given 1 times probability of 1 divided by probability of white. Okay, so everyone clear what I did here? So what I was saying was probability of 1 intersect white, you can write in one of two ways. If you were to just look at this left-hand equation, probability of 1 intersect white is probability of 1 given white times probability of white. But now, this is symmetrical in 1 and white, so if you could swap 1 and white here. Right? So you'd get probability of white given 1 times probability of white. Okay. Now, this is still not in the form that we wanted. And so we can write it in a slightly different way. We could write this as probability of 1 intersect white divided by probability of 1 intersect white plus probability of 2 intersect white. Right? Because we either pick bin 1 or we pick bin 2. Right? So if white showed up, it's either because we picked bin 1 and we picked a white ball, or because we picked bin 2 and we picked a white ball. Right? Those are the only two alternatives. Right? So if you want to see, here's our probability space. Here's the event that we picked bin 1. Actually, maybe I'll draw it like this, because we either pick bin 1 or we pick bin 2. So here's the event 1, here's the event 2. So we either pick this one or that one. And then here's the event that we got white. Okay. Now what's the probability of white? Well, it's this whole area divided by that area, right? And so it's equal to this area plus this area, right? So that's all I'm saying. It's white intersect 1 plus white intersect 2. And now if you write this out in these terms, you get the full form of Bayes' rule, which just says it's probability of white given 1 times probability of 1 divided by, again, this is the same thing as that, so it's probability of white given 1 times probability of 1 plus probability of white given 2 times probability of 2. Okay? So this equation is usually called Bayes' rule. And then once you substitute this piece, this is called the total probability rule. Okay, sorry, the Bayes' rule is this equation, and then okay. But at this point, we have everything in the form that we wanted, because this we know from here, this we know from here, this and this are the same two, and this we know from here. Yeah? Okay. It's clear? Okay, so let's go ahead and do the substitutions and see what the answers are in these two cases. So in the case of primality testing, here's the thing that we know about, in order to know what's the fraction of 200-digit numbers that are prime. So the fact is, if you look at n-digit numbers, if you look at 200-digit numbers, roughly 1 over 200 of them are prime. So if you pick a number at random and it's 200 digits long, roughly 1 in 200 of them will be prime. It's going to be not 200, but 200 times e, which is 200 times 2.7. Okay, so we could say roughly, if you want to underestimate the chance of getting a prime, you could say 1 in 1,000 200-digit numbers are prime. Okay, so in this case, what we have is, so in the primality example, we have p equal to 1 over 1,000, q1 equal to 1, q2 equal to 1 over 10,000. Okay, this was probability of 1. This was probability of white given 1. This was probability of white given 2. And now we want to know what's the probability of prime, which is probability of 1 given white. And now by a formula, this is probability of white given 1, so that's 1 times probability of 1, which is 1 over 1,000, divided by 1 times 1 over 1,000 plus. And now what we need to do is probability of white given 2, right? Probability that it outputs yes, even though it's a composite, which is 1 over 10,000 times probability of 2. Probability that if you pick a number at random, it's a composite. And that's almost 1, right? It's 1 minus 1 over 1,000. So we can just underestimate this number by making this larger. Right? So that's a very good approximation to make. And so that's about 1 over 1,000 divided by 1 over 1,000 plus 1 over 10,000, which is 10 over 11, right? Okay, so you could get a roughly 90% chance by making sure your primality testing algorithm has a chance of making an error on composites, which is 1 in 10,000. Okay? But now, as I said, there's a tunable knob on these primality testing algorithms. So what you can do is, at the expense of running for twice as much time, you can reduce that error by a factor of something. Okay? Okay, so you can... what you could do is have the algorithm run for twice as long, and then what happens to that error is it'll get squared. So instead of 1 over 10 to the 4, it'll become 1 over 10 to the 8. Okay? And the algorithm would just take twice as long. So now you can figure out, well, what's your error tolerance? So suppose you're happy with letting it run twice as long. What do you end up getting here? Well, you just work your way through this again. Okay? And basically, what's going to change? Well, the only thing that's really going to change here is that this 10,000 will be replaced by 10 to the 8. Right? And so you'll get 1 over 1,000 divided by 1 over 1,000 plus 10 to the minus 8. Right? And so basically out here you would get 1 minus, so if 10,000 goes to 10 to the 8, then this number would actually go to something like 1 minus 10 to the minus 5. Okay, I think. Okay. So what this shows you is what the trade-off is, right? How should you run this algorithm? Should you run it for twice as long? Well, how much does your chance of success change as you change the running time of the algorithm? Okay? Okay, so now I won't actually bore you with the calculations, but you can do the same calculations for this drug testing example, and you can work out what's the probability that the person's affected, given that the test comes up positive, and if I remember right, the answer is something like 0.3, maybe. Okay, so maybe that's what it works out to be. And then you can sort of think about it yourself and sort of say, is this an acceptable answer? Is it acceptable to know that you started with knowing that if you were a random person in the population, the chance of being affected was 1 in 20, 0.05, right? And now this test is good enough to increase that bound from 1 in 20 to 0.3. So if it turns up positive, then you know that the chance of having this condition is now up to 0.3 instead of 0.05. Maybe that's really worth knowing. But that comes at a cost, which is there are many, many false positives. Right? And so you have to weigh these costs versus the benefits and say, how good is it to have this kind of a test? Right? And so in order to say that, you really have to solve this inference problem. Okay, so instead of going through that calculation, let me just talk about one other place where this comes up, and then, okay, so this other example is handwriting recognition. Okay, so now in handwriting recognition, actually, the problem is actually a more complex one, and hopefully a few lectures from now we'll see a more complete sort of solution to it. But for now, let's look at one piece of the problem. So suppose that you're trying to tell the difference between two different letters. So there's I and L. You happen to know that the next letter that you're trying to recognize is either an I or an L. You don't know which one. Well, except that from the context, you know that this is much more likely than that. So you know the chance that it's I is 0.9, and the chance it's an L is 0.1. Okay, but now, in addition to that, you have some feature vectors that features that you've extracted, through, this is your computer vision system. It's trying to read those characters, and it's trying to recognize which character it is. So maybe it's trying to detect whether or not there's an I. But of course, as you probably know, detecting whether or not there's an I on top of, whether there's a dot on top of the I is a risky business. People sometimes put it down, and sometimes the I appears over here where it can be confused with a T, and sometimes it migrates all the way where it's completely missing. And so these features are not very reliable. And so you extract these features and you hope for the best. And okay, so what you want to know, so you've extracted a certain feature, and the other piece of data you have is you have some understanding of what's the probability that the letter that you're reading is actually an I, given that this feature is present. And what's the probability? Sorry, no, you don't know this. This is what you want to know. Okay, what you really know is, by analyzing the person's handwriting, what you know is what's the probability that it has this feature, given that it's an I. Okay, so there's some feature you're trying to detect, which is somehow related to the question: is there a dot? Do you detect something which might be a dot? Okay, so you can't even reliably detect a dot, and maybe it's not even there. But what's the chance that this feature is turned on, given that it's an I? What's the chance that this feature is turned on, given that it's an L? So you know these two numbers, and you know what's the probability that you expect it to be an L or an I in that given context. And now, based on this, you want to guess. Okay, so how would you guess? Bayes' rule. Okay, so as you can see, this is a very small toy example, right? And what you really want to do is build upon it, and hopefully, in a few weeks we'll have enough tools to build upon this and say, okay, what does feature extraction really look like? What does this kind of recognition and inference really look like? Okay? Okay. So, any questions? Okay. So, let's see. Okay, so just to orient you, I hope you realize. You must realize, right? Next week is spring break, and then which is very good. And then the week after that is a midterm, which may or may not be good. Okay, so let me just say a few things about the midterm. So I should say that so even though it's cumulative, okay, it's cumulative in terms of concepts, but so in other words, you shouldn't forget how to write things precisely in terms of propositions. You shouldn't forget proof techniques or induction. But it's not that the midterm will be going out of its way to test you on those things. If those come up in the context of the topics that we have, then certainly you should know how to do those things, right? So in other words, if there's a question about modular arithmetic that happens to involve induction, well, so be it. But it's not that we'll go out of our way to find problems about induction that that have nothing to do with the topics that we've covered since the first midterm. Okay, so again, the major topics are model arithmetic, RSA, polynomials, polynomials and error correction, etc. Infinity, diagonalization, and then there's counting and probability, right? Now, the other thing you should realize is since we are actually going to be building upon probability, right? This is this is the material we are going to be if you understand this material in probability, basic probability, that's a really good thing going forward in terms of understanding the rest of the course. So this is a very good opportunity for you to study this material and understand it well. And therefore, it's just to provide you a good incentive for that, probability, this part of the material will be overrepresented compared to the amount of time we've spent on it since the first midterm. Right? Okay, yeah.
So what lecture or what note is the midterm going to cover up until?
Up through conditional probability. Yeah? Okay. So the other thing I should say is that, the first midterm ended up being, I think, at least perceptually a little, somewhat longer than I'd expected it to be. And so certainly you should expect that this second midterm would be, you shouldn't feel as much time pressure with. Okay, so that's going to be the way I'll try to put it together. Hopefully with more success with that this time. Okay. Okay. So I should say one of the things that happened last time is in talking to several students, I realized that there were students who spent a lot of time on the first couple of problems and didn't have enough time for the rest. And there were also students who didn't take very seriously the fact that we said, don't try the last problem until you're satisfied you spend as much time as you want to on the rest, right? That wasn't it was supposed to be a harder problem. Maybe we'll be a little bit more clear about that labeling just to make sure that you have, perhaps we'll put up, if we can print it in color, we'll print up a color sign saying, warning, don't do this or don't go there. But by whatever means, we'll try to warn you off those problems and say, okay, just don't do this unless you're, okay? Okay, any questions? Yes?
Do you have policy shadowing? If you know the final, it shadows the midterm score?
No. Yeah. I suspect I didn't hear your question completely, but I think I did. So, yes. Oh my goodness. Yeah. We didn't, did we? I think the default was we were going to push it towards the final if we can't think of anything else. There've been times during the semester when we thought that it might be a good idea to have these points be somehow participation points, but unless we can figure out a good way to assign them, let's say that. So, what do you think? Are we already beyond the stage of? Yeah. Okay. So for now, let's just think of it as being final, unless almost certainly. Okay. Yeah.
When you say conditional probabilities, when you have a midterm, does that include inference?
Yeah. Bayesian. Yes. Uh-huh. So think of the final as containing everything that's covered through this last homework, right? Yes. Sorry, is that the same question about the shadow? Yeah, that's what I thought, but I'm not certain. Okay, so let me just say about this, since this question came up a number of times. So the question was whether there's a way to recover points if you've done badly on the first midterm. You know, could your second midterm be substituted or final for whatever? And so I don't want to go there because, you know, just creating a formula for saying substitute this for this, well, it's not clear it makes so much sense, because then why wasn't, you know, that's just more or less like reweighting the different midterms and the different exams. What I will do is, you know, since the course is about learning, you know, so if somebody did really poorly on the first midterm and it's clear from how they performed in the rest of the course that they really learned something, you know, that conceptually they made a leap, well then, you know, to the extent that I can figure it out, then I'll in those cases I'll try to bump up the grade. Okay, so it'll be done informally. It'll be, you know, I'll be trying to figure out, well, you know, instead of just using a formula and saying, well, let's substitute this for that, that's just a reweighting. But if it's completely clear that somebody really, you know, they learned a lot, well then, you know, they shouldn't be artificially held back because they started off badly. Okay, so I'll try to take that into account wherever possible, and you know, I'll be trying to do inference, but as you know, it's a noisy process. So, okay. Any other questions, concerns? Yes.
I lost a wallet.
Oh.
Last week, so if anyone saw it.
Okay, so let me actually announce it. So, in case you couldn't hear him, he lost his wallet in this room last week. Was it Thursday or? Okay, so if anybody has found said wallet, please. Okay. Yeah.
So like probably by this weekend, would I be able to like get some kind of practice on it?
So can we? So maybe can we put up? You know, past exams and practice problems. So, yeah. So we'll try to do that. Yeah. Okay. Good. Let's resume. Okay, so let's use conditional probability to explore one more example. Yes?
Can we postpone the homework to the week after spring break?
This particular homework? Yeah, unfortunately no, because it's helpful for you to submit this homework, to turn in this homework and then get the solutions, because this homework is covered in the midterm, right? So it wouldn't do you good to turn it in afterwards, because you should really be practicing it now, right? Yes?
What about people who will not have an internet connection coming Saturday onwards?
Right, so this is why I deliberately made the homework a little bit shorter, easier, so that the assumption was you'd finish it by Friday, but then, but then we, because people are used to turning it on Monday, we said, okay, let's let the deadline be Monday, but in terms of the amount of work, you're supposed to be finishing it by Friday, yeah? Okay, yeah. Oh yeah, the self-grading will for this homework will not be due until the week after spring break. Okay, so basically, the thing is designed so that we can release the solution. So we try to pick it so that, first of all, those of you who need to, if you're going away for a spring break, if you want to have a nice vacation, you finish it by Friday, you turn it in, and then in terms of looking at solutions, you'll get them by Monday. You can study for the midterm, and then the following week, after you come back after the midterm, you can do the self-grading. Okay, so that'll be for later. Okay, so now let's look at one more example of conditional probability, which is secret sharing. Okay, so let's say you're doing a secret sharing scheme, which means what? Well, there's a secret, you're working mod Q, let's say. There's a secret S. S is a random element between 0 through Q minus 1, right? And S is uniformly distributed. So the probability S is equal to anything, any number between, right? So the probability S is equal to A is equal to 1 over Q, right? For every A between 0 and Q minus 1. Okay? That's what it means for it to be a secret. It's uniformly distributed, right? So when it's uniformly distributed, we think of it as something that we have no information about, right? So if I knew that the probability of 0 was higher than the probability of Q minus 1, that's information that I have, right? So suppose that I knew that suppose I didn't know the secret precisely, but I knew that most likely, 90% with probability 90%, it's between 0 and Q over 2. Well, that's a lot of information to have about the secret, right? So saying that I have absolutely no information about the secret means saying that it's completely uniformly distributed. Okay. All right, so now what do we do in a secret sharing scheme? Well, we pick a polynomial of some degree. So we have a polynomial p of x of degree d, let's say d is equal to 2. Okay, so now we have this polynomial. Here are other points on it. Okay, and now if the degree is d equal to 2, what we know is, and we give out these points, right? So there's person 1, 2, 3, 4, 5, 6, 7. All of them, each of them has been given a share of this polynomial. By share, I mean the value at this point. Right? So person 1 gets this value, person 2 gets that value, etc. And now, what are we claiming about this polynomial? What we are claiming is, as long as you have 2 or fewer people who get together and they look at their values and they try to guess what S is, they have no information. Meaning, the probability S equal to A, given that you know what P of 1 is, and maybe what P of 3 is. So you know the value at 1, you know the value at 3. Okay? What do we know about this probability? It's exactly 1 over Q. Right? But now, what do we know about the probability S equal to A given P of 1, P of 3, P of 6? What's this probability? Is it 1 over Q? So what are the only possible values it can take on? Is that 0 or 1? Right? So it's either equal to 0 or 1, depending upon, well, whether S equal to A or not. Right? Because once you know the value at 3 points, you know exactly what S should be. Right? So you know that, maybe you know that S is equal to 5. And now if A equal to 5, then the probability is 1. If A is not 5, then the probability is 0. Right? So as soon as you see the value at 3 points, that's it. You know, this probability, this conditional probability has become 0 or 1. Right? Before that, this conditional probability is exactly 1 over Q. Okay? Okay, so let's look at it in another way. We say that two events are independent. A and B are independent if and only if probability of A intersect B equal to probability of A times probability of B. Okay? So the canonical example of this is coin flips. So let's do it. So if we denote this as our probability space, this is omega. Okay. And let's suppose that this is our event that, so we are flipping a coin twice. This is the event first coin flip equal to heads. Right? So that must be the event that the first coin flip is tails. Right? Now, if we flip another coin, if we flip the coin a second time, these two are independent events. Okay? And the way you should think about in order to see how you should think about independent events, so these events A and B are independent, another way of saying it is probability of A given that B happened is the same as the probability that A happened. Okay? So if you know that B happened, it doesn't tell you anything about whether A is going to happen or not. Right? So, or vice versa. So if you flip the first coin and it turned out to be heads, it tells you nothing at all about whether the second coin flip is going to turn out to be heads. That probability remained unchanged. So now you can see where this came from. See, because probability of A given B is probability of A intersect B divided by probability of B. This is probability of A. And now you just take this to the other side and you get that rule. Right? So that rule is saying exactly that knowing that B happened tells you nothing about A. Similarly, knowing that A happened tells you nothing about B. Right? Okay, that's what independence means. And now, if you want to see it pictorially, you want to see how should you draw B on this? Okay, so how should you say the second coin came up heads? Well, one nice way of drawing it is like this. This is what second coin flip equal to heads might look like. And now you can see that once you know that A happened, once you know that the first coin flip happened to be a heads, what's the probability that the second one is heads? Well, it's this area divided by that area. But that's the same thing as this area divided by the whole area, right? Just by the way I drew it. So knowing that the first coin flip is heads didn't change the probability that the second one is heads, right? The probability the second one was heads was this blue area divided by the whole thing. And now when you cut down, when you say, I happen to be in this case where the first coin flip was heads, well then it's still the same proportion. If the first coin flip was tails, you're in this region, but it's still the same proportion. Right? So the conditioning doesn't change anything. And that's what it means for these coin flips to be independent. Okay, so now, suppose I do this. Suppose I flip these two coins. Okay, so A and B are, A is equal to the event first coin flip equal to heads. B is the event second coin flip is heads. And now I create a third event. My third event is C, which is both coin flips are the same. Either they're both heads or both tails. Okay? And let's say that these are fair coins, right? So what we have is probability of A is half, probability of B is half. What's the probability of C? I'm sorry? 1/2, yeah. How do you see that? Yeah, so the sample space has four points in it, right? So what's your sample space look like? It's heads, 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 tails, tails, heads, tails, tails. Right? There are 4 sample points. Of them, how many, what's C? It's heads, heads, and tails, tails, right? So it's 2 out of the 4. They're all equally likely. So probability is 1/2. Now, we know that A and B are independent. Okay? What about A and C? Are they independent? Given that A happened, do you have any idea whether C happened or not? Right? Well, A happened, you know that the first coin flip was heads. Does that make it any more or less likely that they're both the same? No, right? Because if it's heads, then you're in this part of the space. It's still equally likely that they're going to be same or different. If it's tails, you're in this part of the space. But it's still equally likely whether you'll get same or different. Okay? So here we have a case where A and B are independent, A and C are independent, B and C are independent. But what about A and B and C together? Are they independent mutually? Well, no, because as soon as you know whether A and B occurred, you know whether C occurred. Right? So the probability of C given A and B both occurred is not the same as the probability of C. Right? Once you know that A and B both occurred, well, you know both of them are heads. So you know that C definitely occurred. So the probability of C went from 1/2 to 1 here. Right? And so this is a case where you have pairwise independence. Every pair of these are independent, but the 3 together are not. Right? Now, what happens in the case of these polynomials, what makes them so interesting is that they have this kind of limited independence. So what we said here about these polynomials is, if you have a polynomial of degree d, and now you look at its values through a cardboard cutout, and then through this cardboard cutout, if you pick a random polynomial and you ask, what's the value at 0? Well, it's uniformly random. Right? If this was a random polynomial, S is going to be completely random. It's going to be 0 or 1 or q minus 1 with equal probability. Okay? What about the second one? Well, it's uniformly random as well. What about this one? It's uniformly random as well. Okay? All right, but now let me look at 2 of them together. Again, they're both going to be random. So it's going to be as though I picked S uniformly at random and I picked P of 1 uniformly at random, independently of each other. What if I look at 3 of them? Still random. Right? It's as though this was picked randomly, this was picked randomly, and this was picked randomly. Now what if I look at 4 of them all at once? Now the fact that it was a polynomial of degree d equal to 2 comes up. right? Because as soon as so if I look at these four, as soon as I look at these, as I know these first three values, I know exactly what the fourth one is. So the fourth one no longer looks random given the first three. Okay? So these polynomials of degree d have this magical property, which is that you can make any cardboard pattern, cutout pattern that you want. Right? So you make any pattern that you want, where your cutout pattern actually looks at this guy, and that one. Any three of them. Right? So let's say everything else is hidden from you, only these blue parts are available to us in this cutout. And now we pick the polynomial at random, and I show you what the polynomial looks like. You would have no way of telling, right, that this was a polynomial, whether this was a polynomial that I picked, or whether I just picked these points at random. Right? So I could pick this one at random, this one at random, this one at random independently. You would have no way of knowing whether I was doing that, or whether I actually, honest to goodness, picked a polynomial of degree 2 at random and showed you its values. Okay? You don't know what's happening behind the scenes, because this is, any 3 points are uniformly random. Right? They're independent and random. But as soon as you make one more cutout, you look at 4 things, then you can tell the difference very easily. Right? Because if I pick all 4 points at random, the chances that they lie on a polynomial of degree 2 is very small. Actually, you can calculate what it is, I hope. Okay? But on the other hand, right, you know what it is. Whereas if I pick a polynomial of degree 2, then when you see 2 or 3 of these points, you know exactly which polynomial it is. So you know that this last point has to be this one. Right? So if it was a completely random point, its chance of lying on this polynomial would be exactly 1 over q. Right? So you have a way of telling the difference. We're back in that situation. Right? In the one case, it would pass with probability 1. In the other case, it would pass with probability 1 over q. So you can tell the difference. You can infer which one it is. Yeah? Okay, so this is this property of limited independence. Okay? And this is what makes polynomials so powerful. Magical, right? This is what gave us all these properties of polynomials. Okay, let's do one last thing before we end. But before that, are there any questions about this? Yes?
So if you weren't told that it was a polynomial of degree 2,
Yeah.
you just pick random points, there would be no way to figure out if the fourth point should be random or not.
If you did not know that it was if you didn't know it was a polynomial of degree 2, but what was the condition you were given?
And you're given, you see the 4 random points.
Yeah.
Would you still, there would be no way.
Well, let's say that you're doing this experiment, right? You're looking at these values. They appear. You have this small window through which you can look at it, and you happen to look. Your window consists of 4 slots. And so you're viewing these 4 points, but this pattern keeps getting updated. Let's say that this is one of these neon signs, and it happens to show you this curve. Behind the scenes, there's this curve, but you only happen to see 4 points on it. But this curve keeps updating every couple of minutes, and so you keep watching it. And as you're watching, you're bored, so you do the calculation, and you figure out, well, every time you see it, it happens to be that that there's a polynomial of degree 2 that fits it. Then you'd be pretty sure that these points are not being picked at random, right? It could be that they were being picked at random, and it just happened to be that it happened to fit in, but the chance would be very, very small. Right? On the other hand, it could also be that everything just lies on a straight line, and then what's the chance of that if it wasn't really a polynomial of degree 1, right? So. Okay? But the point is, if you don't see any such pattern, it could still be that this is a polynomial of degree 3 that was being picked. It could be that it was a polynomial of degree 3, and if you see only 4 points, it looks completely random. You don't see any pattern at all. There's no information at all that it's a non-random thing with a polynomial of degree 3. So until you see the next point, you have no idea whether it's random or whether it's a polynomial of degree 3. And that's the amazing property. Yeah? Okay, so let's do one last example of conditional probability, which is something called the Monty Hall paradox. Okay. Okay, so this is a paradox which is named after a game show, which maybe sometime in the 60s, which was called Let's Make a Deal. And, this part of it, this part of the narrative was a small part of the game show. But in some of it, what the host was Monty Hall. And this was a program where it was a game show where Monty Hall would give away prizes. There was a game that was played, and if the contestant won, then the contestant would get a prize, and if not, there was they'd get something else. Which, in the case of this particular game, the prize was a car, and the something else was a goat. Okay. All right, I'm not completely clear whether the goat was just a placeholder saying you don't get a prize, or whether the prize was a goat. So it's not completely clear to me, but okay, so the way the game was played is there were 3 doors, and there was a car behind exactly one of them. So one of these doors, there was a car behind, and behind the other 2, each of the other 2, there was a goat. The contestant would pick one of the doors, let's say this one. And then at this point, what Monty would do is he would open one of the other doors that the contestant did not pick and say, by the way, let me show you. Here's a door that you didn't pick, and the car is not there. So he'd open the door and show that there was a goat. Okay? And then he'd say to the contestant, do you want to change your mind about which door you've selected? Okay? And so the question is, if you were the contestant... Okay, by the way, this was one of many, many different variants on what he would do. But this was possibly but that's the... this is the setting of the paradox. The paradox says, well, suppose you were playing this. What should you do? Okay? Yeah. So there are 2 strategies. One which would say, well, look, the prize was behind one of these 3 doors. Now one of them is eliminated. And so there are 2 possibilities. They're both equally likely. So, of course you could switch, or you could stay where you are, and it's all the same. Okay, so possibility 1 is it's 50-50. There's, you could switch or not switch. It doesn't make any difference. The second way of thinking about it is, well, look, when you started off, the probability that you got the prize was 1/3. Right? And now nothing changed behind this door. It's either got the prize or it doesn't have the prize. So your chance of winning here is still 1/3. But now among the other 2 doors, you know that it's not behind this one. So it's obvious that the rest of the 2/3 probability must belong to the other door. So it must be 1/3, 2/3, and therefore switch. Okay? So the question is, which one should it be? So, back in 1990, my colleague Harry Lewis at Harvard was writing a book in which he wanted to include this paradox. And so he wrote to Monty Hall asking for permission to include it, thinking about copyright. So the response came. It said, "Well, dear such and such, I'm sending you my okay for the use of the Monty Hall paradox. I should like to ask you a question. You mentioned that in Part A, the player should switch doors even without additional compensation. Indeed, the player should be willing to pay Monty up to $21,000 for the privilege of switching, or, whatever the price was, you work it out somehow. Now, I'm not well versed in algorithms, but as I see it, it wouldn't make any difference after the player has selected door A and having been shown door C. Why should he then attempt to switch to door B? The major prize could only be in one of the three doors. He has made a selection of one of the doors. He has been shown one of the doors that contains the booby. Ergo, the major prize will be either in the one he selected, door A, or the one that remains, door B. Why would he be compelled to switch doors and even pay for the privilege? The chance of the major prize being behind door A have not changed. He still has one of the two remaining doors. What makes door B such an attraction? I'd be pleased if you would write me explaining the situation. Best of luck with the book. Sincerely, Monty Hall. Okay, so that was his response. Now, actually, if you're interested, in 1991 there was a New York Times article about this, where Monty Hall had a lot to say about it, and you could compare that to this particular letter and see what he had to say. Now, the way to think about this paradox, by the way, I would suggest you think about this. It's a very interesting paradox to think through. But really the way to think about it is conditional probability. Okay, so here's the sample space. The sample space looked like this. There's three possibilities. Either the prize was here, here, or here. Okay? Now, let me contrast two different situations just to make it clear that why the answer is switch or stay the same. So I'll show you two different situations, in one of which you should switch, in one of which you should stay the same. So possibility number one. So let's see. Possibility number one. Let's say that the contestant picked this particular door. So this is the one the contestant picked. And now, possibility one is we don't play this game, the one that I described to you. Instead, it so happens door number 3 is stuck for the moment, during this opening phase. Okay? And so what Monty is going to do is he's going to open door number 2 no matter what. Okay? And it just so happens that when he opens the door, the prize is not behind door number 2. Now, should the contestant switch or not? He should. Okay, so let's look. He opened this door. The prize was not behind it. Okay, so he opens this door, no matter what, and we want to know what happens conditioned on the fact that the prize is not there. Once we know the prize is not there, we know conditioned on that, our probability space now looks like this yellow space. That's all that's left of it, right? Because he happened to, we know that he opened this door and something happened. We observed that the price was not here, so this possibility disappeared from view. Right? We conditioned it away. Right? Because we opened door number 2, he opened door number 2 not knowing what he would see there. It so happened the prize was not there. Therefore, this could not have been the possibility. So now you're left with only these two. Condition on being in this, what's the probability the prize is behind door 1? It's a half. What's the probability it's behind door 3? It's a half. So it doesn't matter whether you switch or not. But remember, what happened in the actual paradox, the way we stated it, is Monty knew where the prize was. Okay? And what he did was the contestant chose a door, and then Monty said, let me open a door behind which I know that the prize is naught. Right? Since there's only one prize, and there are two other doors, there's at least one other door which does not have the prize behind it. Okay? So in each of these three cases, Monty can open some door and demonstrate that the prize is not there. So conditioned on his opening the door, all three cases stick around. Nothing is eliminated. Okay? So you're not, the fact that he opened the door doesn't change the sample space at all. Because he knew where the prizes were, and in each of the sample points he could do something. Right? This was consistent with what actually happened. So the observation you made, he opened this door, there was no prize there, that doesn't make any difference. All the sample points are still there. The probability space is still the same as it was before. And so now, given that it's the same as it was before, what's the probability the prize is behind this door? Well, there are three possibilities. It's only 1 in 3. What's the probability it's behind? Well, he opened one of the other two doors. So now where else could it be? So if it's 1/3 here, right? Where else could it be? Well, it depends whichever was the other door that was not open. So in this case, this would be the open door. So this would be where the prize is with probability. Yeah. In this case, it would be here, right? So you would switch either here or here, but in both cases you would get the prize. But the two cases together have probability 2/3, so you should switch, right? So with probability 1/3, you'd switch to this one, and with probability 1/3, you'd switch there. But that's all part of the problem. It just follows from whatever Monty did. Okay? So, good.